So when you're determining oxidation numbers, there are a few rules that you should remember. One is that if an individual atom or element if it has a charge, then the oxidation number will be equal to its charge. And two, if a group of atoms or elements forming a compound if you have a group of atoms, then the overall charge will equal the sum of the oxidation numbers of the elements that are involved in that group. So, for example, if I have a Cl minus, just one individual atom, if I know the charge, then the oxidation state has to be a -1 because its oxidation state has to be equal to its charge. If I have a magnesium 2+, then its oxidation number is going to be 2+. So, if I have a compound that involves charged elements, and I can determine from the formula what the charges are, and I can recognize that the magnesium needs a 2+ to make its noble gas configuration, and that's why I have 2 Cl minuses so that the overall charge is equal 0. That also allows me to see what the oxidation numbers should be. So if I can determine that the elements present are charged, their oxidation number should be equal to their charge. If the elements are sharing electrons, then those rules kind of don't cover the situation. So if I have like an OCl2, and I can tell that there's no metal involved, and none of the individual atoms are maybe charged individually. Even if they are charged, if they're involved in sharing electrons, I can't just look at the formal charge on the atom and say that that's its oxidation number. If they're involved in sharing electrons, for atoms sharing electrons, I've got to apply the method that we talked about last time, where I assign electrons to the atom. So in that method, if I have a compound that I can tell that some of the elements are sharing electrons, I would draw a Lewis structure and then assign the electrons for oxidation numbers, which is a little bit different from assigning the electrons for formal charge that we talked about in Chapter 7. But then I would apply the formula. So I would apply this new method to assign electrons and then apply the formula for formal charge to determine the oxidation number. So for this part, assigning electrons, the idea here is I assign all shared electrons to the more electronegative atom. And that's the difference between determining oxidation states and determining formal charge. If I'm determining formal charge, I assign the shared electrons evenly, one to each atom that is involved in sharing them. Right? Because the formal charge formula is the number of electrons it normally needs to be neutral minus the number assigned. And for formal charge, that's all the lone pair electrons plus half of the shared. for oxidation state, it's the same formula, but I'm assigning the electrons a little bit differently. Instead of taking these shared electrons and splitting them up evenly, I'm assigning half the shared electrons to chlorine and the other half to the oxygen, which is what I would do for formal charge. For oxidation number, I assign all the shared electrons to whatever element is more electronegative. Since oxygen is slightly more electronegative than chlorine, I would assign both those electrons there and both these electrons here. So now for the oxygen, its oxidation state is going to be the number of electrons it normally needs to be neutral, which is 6 because it's in group 6A, minus 2, 4, 6, 8 assigned to it. That gives it a -2 oxidation state. That's not a formal charge. It's not necessarily unstable because of that. It's just in a situation bonded to elements that are less electronegative than it, so there's an excess of negative charge assigned to it due to its electron density, its ability to pull electron density toward itself. So then for each chlorine has 7 it needs to be neutral because it's in group 7A on the periodic table, and I'm only assigning 2, 4, 6 to each chlorine, so that's going to be a +1. So let's look at another example. Let's look at this one. KMNO4. I've got potassium involved in a compound where there are some nonmetals. So I can predict, given where potassium is on the periodic table, since it's in group 1A or 2A, it's very easy for potassium to lose an electron and make the same number as a noble gas. So I would predict that the charge on the potassium would be a plus, and that the charge on the rest of this would have to be a negative. So that allows me to say, right off the bat, that based on this rule here, that the potassium has an oxidation state of +1, because that's its formal charge, and it's an element that's not sharing electrons with the other elements. It's just there because its positive charge attracts the negative charge on the other group of atoms. But the other group of atoms is probably involved in some sharing, so this is tricky. We haven't really talked about these types of bonds in detail, but some of these metals, like manganese, that are in the middle of the periodic table can form bonds with nonmetals that do involve some degree of sharing. Those are called coordination bonds, and that's a topic that you go into detail in general chemistry too. So if we recognize that there's some degree of sharing there, we can analyze that as we normally would, but really that's not even totally necessary, because whether the manganese is sharing electrons with oxygen or whether it's not, and the oxygens have the electrons all to themselves, and I've got 4 of those, either way I can assign the same oxidation state to the manganese. So how do I do that? Yeah, I have to recognize that this piece where they're combined has an overall -1 charge. So if I add the oxidation states for 4 oxygens and 1 manganese together, it has to sum up to -1. Right? So that's rule 2. If I have a group of atoms, then the sum of the oxidation states for the atoms involved in that group is equal to the overall charge on that group of atoms. So if the overall charge is -1, and even if I imagine the oxygen sharing these electrons, when I have shared electrons and I'm doing oxidation states, I shift the shared electrons all to the more electronegative atom. By that analysis, whether they're sharing, they would get a -2 oxidation state, or whether they're ions making their noble gas configuration without sharing, they still get a -2 either way. So if I've got 4 of those, each one having a -2 oxidation state, and this overall adds up to a -1 because that's its charge, what must the oxidation state be for the manganese? It must be a +7. +7 minus 8 gives me a -1 overall. So I can determine the oxidation state in that compound for the manganese to be a +7 and for the oxygen to be a -2. Questions about that? I've got 4 oxygens that each have a -2, so the combination of those 4 adds up to -8, and that's why I need a +7 on the manganese so that the sum will be -1, which is the charge on the overall group. Other questions? Okay. You could. I don't think that will necessarily work every time, but if, like, say you were working on the final exam and it's a timed exam and the time was just about to run out and you just had that one last question and you didn't have time to go through the full analysis, you could maybe guess at that. There are other oxidations. There are many other oxidation states for manganese. Manganese is like a classic example of a compound that can adopt a great number of oxidation states. So if you take KMnO4 and you react it with something, it does react as an oxidizing agent, meaning it likes to put oxygens on carbons and things like that. And after it reacts as an oxidizing agent, oftentimes you see MnO2 produced as a product of that reaction. And so if you were to look at the MnO2, and imagine how that oxidation state would be. Again, since the oxygen's more electronegative, you would assign the electrons there. So that gives you a -2 for each oxygen. And this overall is neutral, so the manganese would have to have a +4 oxidation state in that case. So there are lots of compounds. Those transition metals in the periodic table can often get involved in compounds with a variety of oxidation numbers.